Hi everyone. Thanks. It's an enormous pleasure and honour to be speaking at this meeting. What I wanted to talk to you today is kind of a mix of some thoughts I've been having about metaphysics and its role in science and philosophy of science. But I also want to talk a bit about some of the work I've been doing in philosophy of physics, and that work's been done, a lot of it with Sean Gribb, who's a theoretical physicist, and then also with Radin Dardashti and Eric Winsberg, who are philosophy of physics, philosophy of science. But I also want to thank Eric for innumerable discussions and the aforementioned beer colour that are related to various points that I'll talk about today. So I wanted to start with something very familiar to a lot of you. It's a quote from a paper by Howard Stein from 1989, yes, but, the issue between realism and instrumentalism seems to me not to be clearly posed. And what I really believe is that between a cogent and enlightened realism and a sophisticated instrumentalism, there is no difference that makes a difference. So, this seems like an odd thing to say, or at least to many people, who probably haven't read this paper would find it an odd thing to say. Philosophers of science habitually assume there's a good ground for maintaining a difference between realist and instrumentalist views of scientific ontology, science in general. Particulars assume that traditional realists would assert and instrumentalists deny that terms like electron and space-time genuinely refer. It's a well-posed debate to be had. So what I'd like to do first is situate Stein's arguments that it isn't a difference that makes a difference in the context of related skeptical remarks by Blackburn and Price. And I'm drawing a reasonable amount here from a very nice paper by Carl Stanford, which is where I was first made aware of the connection between the Blackburn and Stein. So after I've done that kind of situation, I want to use some of the work I've done over the last few years to try and maybe draw some morals about how we can understand where we get to. So according to Stein, and I'm going to read a little bit for the first half of the talk, and then hopefully when the second half can be a little bit less quotey. So according to Stein, the idea that a theory is nothing but an instrument for calculating the outcomes of experiments involves a tacit implication that experiments in question form a rather special domain. And he offers this very nice example that he was made aware of by Eugene Wigner, that it's often claimed that one ever does in quantum theory is calculate the results of scattering processes. But according to Wigner, while this is almost true, it's not quite true. One also uses quantum theory, for example, to calculate the density of aluminum, I should say. Eric actually had to correct my spelling because my autocorrector changed this to English spelling. I'll try and make sure everything's pronounced and written in American when it's a quote from Howard. So he continues later in the paper. The trite form of debunking instrumentalism makes a false estimate of the scope of the theory as an instrument. It's no longer appropriate to speak of simply calculating the outcomes. So rather than this kind of naive, simplistic instrumentalism, what Howard Stein puts forward is this, what he calls sophisticated instrumentalism. And in this sophisticated view, we kind of enrich the things that the theories are instrument for to include things like representing phenomena. And then he goes on to really, I think, make one of the crucial points of the paper, that the semantics of reference and truth through a given theory is itself a theory. One who considers theories in general to be mere instruments need have no hesitation and no qualms of intellectual conscience in accepting this theory as an instrument, that is, a theory of reference and truth. So this is a kind of, on the one hand, enriching instrumentalism to this sophisticated variant where you can help yourselves to things like reference, truth, representing phenomena. On the other hand, the realist might object that the instrumentalist is kind of like doing something illegitimate, and that really this is not what the realist meant by realist semantics. That she meant semantics not as a mere instrument, but as genuinely giving real or true reference to the theoretical vocabulary. So once the realist wants to claim this, the question is what are they substantively claiming more? And the idea is to push the realist back into something like what Stein calls the fallacy of something more, or the problem of the noumena. So, two straightforward objections to this move to try and pour cold water on this debate, by both enriching instrumentalism and then kind of showing that realism has to sign up for some kind of solution to the problem of the noumena in order to distinguish itself from this enriched instrumentalism. So objection number one, which I'll call the straw man, the idea is that the realist is responding, no, you're not even criticising my view. Modern scientific realists actually don't rely on solving the problem of the noumena, rather they make use of inference to the best explanation. So realists need not commit the fallacy of something more in order to distinguish themselves from instrumentalists. And this is pretty much anticipated already in the paper. The second objection is one of incoherence. The instrumentalists can't consistently disavow semantic notions, as this corresponds to self-contradictory denial that the relevant term or sentence in question is semantic property. So what I want to do is use Blackburn to knock out the first one and Price to knock out the second. This is Blackburn. A reasonable realism needs some kind of reinterpretation. On this view, we treat realism not as involving any transcendental comparisons, i.e. committing the fallacy of something more, but as itself an explanatory hypothesis on all fours with other theoretical explanations already common in science. The plan, then, is to turn what seemed like a transcendental doctrine of doubtful meaning into a piece of natural explanation, accessible as other scientific explanations are. For the cosmic coincidence of events falling out as they do, time after time, realism substitutes the cosmic coincidence of reality being continuing as it is, time after time. If the problem is that of understanding why patterns of nature have no discernible limit to their shelf lives, it scarcely adds to be told that they are the outcome of things and laws that themselves have no discernible limits to their shelf lives. The correspondence between science and reality cannot just be given a use by giving a given explanatory drapery. Such a move would be taking an apparently transcendental notion and announcing that it has a further explanatory role. It's not that there's a further set of data about science and success that requires something like an independent sideways explanation. It's just that the very regularities in the phenomena that required the theory in the first place should now be looked on as including any success we have using the theory. So the idea is that this kind of IB-style motivation for realism in the end is going to fall back into committing the either not having any content or committing the fallacy of something more, just like the transcendental realism. So how do we want to respond to the incoherence charge? And so here I wanted to draw on Hugh Price. He's written quite a lot of related work, in particular from an essay that's in his 2011 book called Naturalism Without Representation. Where I think, although he's talking about a particular view of deflation, like kind of naturalistic, deflationary view of truth, I think you could use a lot of the same arguments in the context of sophisticated instrumentalism. Deflationism about truth and reference blocks access to the kind of semantic ladder needed to transform a theoretical question about terms into a question about their assumed objects. Deflationism offers a broadly scientific hypothesis about what linguistic creatures like us do with terms such as true and refers, what role these terms play in our linguistic lives. And I'll use any Australian pronunciation for anything. Okay. So Price continues. Boghossian argues that irrealism about semantic notions is incoherent because irrealism involves precisely a denial that the term or sentence has semantic properties. However, the point turns on the fact that so constructed irrealism relies on the kind of theoretical framework provided by the representational view of language. So long as a semantic deflationist simply rejects this theoretical framework, the position is not incoherent. Deflationists can consistently offer a use-explanatory account of semantic terms while saying nothing of theoretical weight about whether the terms refer or have truth conditions. The answer to Boghossian's challenge to deflation thus depends on the distinction between denying in one's theoretical voice that terms refer or have truth conditions, and being silent in one's theoretical voice about whether these terms refer or have truth conditions. A deflationist can, indeed must, do the latter, having couched theoretical claims about the terms concerned in other terms entirely, and having insisted, qua deflationists, that the semantic notions do no interesting causal explanatory work. So, by mocking up this argument, I wanted to get to a particular place where we can actually start thinking about a positive story about what the sophisticated instrumentalist does want to do with the metaphysical or would have been referential parts of scientific vocabulary. So how do we go about couching theoretical claims about reference or truth or ontology in use explanatory terms? And so my particular challenge coming from this motivation for the liberalized instrumentalist is to give an adequate approach to scientific language where we can give a positive non-semantic story about what role metaphysical posits are playing in our semantic lives. And so this is it would be a huge project. What I want to do is offer two examples in the context of these three hypotheses. So my three hypotheses are as follows. Diachronically, the principal role that metaphysical posits play in scientific language is heuristics for future theory construction. Or I was thinking just now, maybe not even future theory construction, but future theory articulation. We don't just construct theories, we also refine and rearticulate. Synchronically, the principal role that metaphysical posits play in scientific language use is to ground inferential practice, and both in theoretical context, but also what we'll talk about a bit later in experimental context. And then this is my slightly controversial final hypothesis, is that plausibly metaphysical posits that don't play either of these roles, we should just ignore them in scientific discourse. And they shouldn't be part of mature philosophical discourse about science either, at least so far as we sign up to liberalized instrumentalism. So what I want to do in the rest of the talk is give you two examples of this idea, one relating to the heuristic notion, one relating to the inferential one. And the heuristic one I want to talk about, which links quite nicely with a lot of the things that Oliver was talking about, is the role of ontology of time in quantum gravity. In particular, the way that we think about ontology of time classically, how that can be heuristically useful for quantum gravity. And the second thing, if I have time, is I want to talk about the role of a metaphysical posit inferentially in context of multiple realizability and Hawking radiation in analog gravity, so in black holes and analog black hole systems. How am I doing time?
You got 18 minutes until the 15-minute mark.
Oh, thank you. Well, maybe I'll try and slow down. Am I speaking too quickly? No. Okay, good. So, temporal ontology in quantum cosmology. As this is something I've thought about pretty much most of my professional career. And this is my very simple way of trying to illustrate something that it's taken me a long time to get to this level of simplicity. So if we think about different notions of time, and we kind of start off with Newtonian notion of time, and these could be notions of time, we're defining them in a relatively theory-independent way. But you could actually use simple particle models to cash out all of them without having to go full on relativity theory. So let's think about absolute time, and I suppose the person embodying this would be Newton. Whether this is actually fair in Newton's view, I'm not going to say anything for this audience, but think about this like Newtonian time. So in Newtonian time, what do we have? We have absolute duration, and we have absolute succession. What do I mean by this? I mean something very precise. I mean, we have a metric structure for time, and we have a monotonic parameterization of time. I specifically do not mean anything like arrow of time by succession. What I mean is that the ordering of times can't go back on itself. So there isn't a kind of directed ordering, it's just the ordering, it has to be consistent. So if we think about the amusing way of putting this that pointed out to me in Geneva a few weeks ago, if you think about some kind of events, lunch, dinner, beer, sleep, I'm not saying we have to go lunch, dinner, beer, sleep, or sleep, beer, dinner, lunch. When you're jet lagged, these things can be pretty interchangeable. What I'm saying is you can go either this way or this way, but you can't go, when I'm by absolute succession, what I mean is you can't go lunch, dinner, dinner, sleep, beer, sleep. Right? So the ordering can't go back on itself. But there isn't an arrow of time, there's just a restriction. The way that we parameterize times is monotonic. Okay, this is pretty important for what the rest of us say. So these are the kind of mathematical cashing out of these two notions. Duration in terms of a temporal metric, succession in terms of monotonic parameterization. So let's move on. What other notions of time do we have? We think about relational time, where we can remove the kind of absolute duration structure. We can make, one way of thinking about it is to define the time up to diffeomorphism. Another way to think about it is that we have a reparameterization invariant theory. So we can reparameterize, we can relabel the times, we can change the kind of distance in between times. But we keep absolute succession. And so if we think about Newton as the kind of standard bearer for absolute time, I think we can think about perhaps Julian Barber, at least in his classical work, and maybe Ernst Mach, and I think possibly even Leibniz as defending this relational notion. So then the final option is where we get rid of duration, like relational time, but we also get rid of succession. And I think there's a little bit of confusion when people talk about this view. They often talk about there not being time. But really, I think this is a sense of internal time. And the way that this works is you'd use a particular degree of freedom as your clock. So if you have a system and you have, say, two pendulums, you say the pendulum is the clock, the other pendulum is the system, and you use one degree of freedom to label the changes of the other. And the reason why this is an internal time without succession is because the other system you choose is free to have dynamics that don't mean that the labeling will be monotonic. In fact, invariably, you'll inevitably find in any kind of complicated system that there will be no degree of freedom that won't, as a clock, start running backwards at some point. So the standard bearer for this view is kind of Ravelli. So this is kind of Ravelli internal time, partial observables, evolving constant of motion, blah, blah, blah. You can implement this view in very simple toy model systems. And these are three different views, and I want to argue that the relational time one has advantages in certain respects. In particular, I want to use a very, very simple example, a fairly simple example from cosmology, where you can actually see how this difference makes a difference. So, mini superspaces is an extremely symmetrized, basically as simple as you can make it, FLRW spacetime. So you have homogeneous isotropic spatially flat FLRW, and we have the matter content is just a free scalar field, which is massless, right? You really can't make things much simpler. So we end up with two dynamical degrees of freedom. We have A, which is the scale factor, think about the geometric degree of freedom, and we have a scalar field, which is 5. And later on, I'll switch from A to V, which is just A to the cubed square root. It's just basically like the volume. What you can do is, from the Einstein-Hilbert action, derive a canonical analysis according to the Dirac theory of constraints, or ADM variables, or however you want to phrase things, and then derive a Hamiltonian from the system. The details of this are quite complicated, but in the end, the details don't matter that much for what I want to say. So we have a Hamiltonian for the system. This is actually a constraint, and this here is a multiplier. These are canonical momenta for phi and A, and this is obviously the cosmological constant, which will be important, and I'll say later. So the first thing that's very useful physically about the system is that it has singularities. So you can show, using basically the same argument as the Penrose-Hawkins singularity theorems, that this model generically has a Big Bang singularity. I could graph this in a particular chart, and prove this in a coordinate invariant way as well, but in a particular chart, to kind of nicely illustrate the point, you can see that if we take the spatial volume versus time, the kind of singular time is when the classical solution hits the origin, which is when the volume is 0. And on the same kind of the same singular time, the scalar field is blowing up. So you can see that this is going to be a kind of pathology in the model, and we have singularities in the sense of both the incomplete geodesic and curvature singularities. So this model, so we have a model. It has a feature that's interesting but problematic in some ways, and we have two interpretations of it. We have an internal time interpretation and a relational time interpretation. And we have underdetermination between these two. We can adequately apply either interpretation to this model. What's interesting is that by choosing one of these metaphysical stances, we motivate different procedures for quantizing the model, for having a toy model for quantum cosmology. And the traditional way of quantizing it, and the kind of mainstream view, is to follow something called Wheeler-DeWitt quantization. And that's very closely akin to the internal time notion. There's actually an alternative that I've been working on with my collaborators for some time, which is motivated by the relational time interpretation, and that leads to a Schrodinger quantization. So if you apply the Wheeler-DeWitt quantization, which is kind of motivated by the internal time hypothesis, you get a time-independent equation, which is, you can think about basically like a time-independent Schrodinger equation for this model. That's a bit more complicated. And interestingly, what Ashtekar has shown, at least for simple parameter values, and we're hoping to generalize this ourselves in our work, is that for this model, the quantization does not resolve the classical singularity in the precise sense that classically divergent quantities, the relevant expectation value is also divergent. So we don't get finite expectation. The things that behave mathematically, pathologically, classically, their expectation values in the quantum model are non-finite. They also behave in an kind of uncontrolled way. And one of the great achievements of loop quantum cosmology is to deal with this problem within the Wheeler-DeWitt framework. But that necessitates the introduction of fundamental discreteness, which I won't talk about anymore. What I want to talk about is recent work with Sean Gribb. I say work with, maybe did most of the work, so I'm a little bit bad saying this. So Sean's a theoretical physicist, and we've been working together, me as the philosopher, him as the physicist, on motivating a different way of quantizing these models based upon relational time. We call it relational quantization, and we can show that it leads to a Schrodinger equation from various different methods. What we can do is actually, what we've done recently is apply this kind of procedure for quantizing to keep time evolution to this model, and we can show explicitly that the Big Bang singularity is resolved in our quantization, by which means specifically that expectation values are always finite for the classically misbehaving quantities. So in this precise sense, we can resolve the Big Bang singularity without introducing fundamental discreteness like in the loop quantum cosmology. And so this is a nice plot. We actually look at the expectation value of phi versus the expectation value of v, and we can think of this diagram as representing the ordered succession of correlations between these expectation values. This is what's kind of the relational ontology that we want to say, this is what's fundamental. You can actually see that coming into this quantum region, the red line is the classical value, the blue line is the expectation value. In the quantum region, the two diverge, and the quantum expectation value, the volume reaches a finite minima. So the universe bounces back out of the Big Bang rather than getting to the singularity. Hopefully this will work. Also, there's an interesting sense in which we might identify this period here where the rate of change of expectation of phi with v is roughly 0, is something like an inflationary epoch, and it's something we'll look at, we're quite interested to look at more in the future. So we can actually, one of the things to say is that this regime, the deep quantum regime, the expectation value isn't really very representative of what's going on. So to show you what's the kind of physics of the model, we actually show a little animation that around this period we get a lot of structure, basically from interference between in and outgoing eigenfunctions. Eigenfunctions of what? Eigenfunctions of the cosmological constant. Because one of the key parts of this procedure is actually to treat the cosmological constant more like a constant of motion, so you end up with a quite different phenomenology. And I've got probably about an hour's worth of stuff to say about that, so I'll try and restrict myself. In the end, the story is that by taking this metaphysical posit of absolute succession, we get a new heuristic for quantization. The Big Bang singularity is resolved in this sense, since we have this classical expectation value, and we get new, and interesting, at least to me, phenomenology. So we get interference with the ingoing and outgoing eigenfunctions around the big bounce, which might, in the end, turn into something detectable. We also get superpositions of the values of the cosmological constant. This is making you think a bit of unimodular gravity. It should, because essentially our model is using the same equations with slightly different interpretations to the unimodular approach that Unruh and Wald in particular were developing in the 80s. So the idea is that, seen from a traditional realist perspective, the metaphysical undetermination found in the case of temporal ontology of the classical model will be some really deep problem, because we have two different interpretations that have different notions of time. We try and break the interpretation. Contrastingly, seen from a restricted instrumentalist perspective, the undetermination is irrelevant and uninteresting and boring, because it's really an undetermination of fluff that doesn't really go into the predictive experimental calculation and use of it. But what I want to say is, seen from a kind of Steinian sophisticated instrumentalist perspective, our case study makes much more sense. The kind of diversity of metaphysical interpretations is interesting in the sense that it plays a heuristic role in the scientific discourse. How would you explain that? So the second example I wanted to talk about was multi-realizability in analog gravity. And this is quite a different context, and it's quite a different example, so maybe I have to try and change my headspace. So, as I'm sure almost all of you know, that there's this famous prediction by Stephen Hawking that is based on slightly odd calculational techniques, which I won't go into the details of that too much for the time being. So it's a semi-classical result, and you have, in the end result of the calculations is to associate a radiative flux to black hole event horizons. And exactly how we should understand the kind of connection between the flux and the horizon is still a matter of controversy. In particular, there isn't really a clear and accepted causal story about where the radiation is coming from. In any case, no matter various ways people have done these calculations, they always seem to come out the fact that black holes are hot. They radiate, and they radiate from thermal spectrum. But the spectrum is such that the temperature is absolutely minuscule. We're talking of the order of billions and billions of kelvins, depending on the size of the black hole. So actually testing this, like, without the possibility, which sounds a bit risky, of building micro black holes in the lab, is really not going to be possible. If you think about, relative to the CMB, how faint the black hole radiation is, it's like thinking about a candle, heat coming from a candle against a nuclear bomb. It's really just will be completely drowned out by the CMB. So, in not that long later, Unruh had this idea that we can use sonic horizons in fluids to simulate, or as analogs for, black holes. And perhaps to explain this, do people want me to explain the silly diagram?
Yes.
Okay. So the idea, Unruh was giving a talk about black holes, and he wanted to try and explain the physics of black holes in an accessible way. And unbeknownst perhaps to everyone, Bill Unruh is a big fan of Terry Pratchett, and those of you who know Terry Pratchett's work, it takes place on a disk world where water flows off the edge. And so if you imagine a scenario in which there is intelligent fish living on the lake just before the edge, where water flows off into space for eternity, and they're communicating by sound. We can think about this as analogous to me and Eric living somewhere outside a black hole event horizon and communicating by light. And then the idea is, if you imagine me falling into the black hole and I'm signaling Eric as I do, the last kind of photon never reaches Eric at an infinite time as I cross the horizon. And the idea is that conceptually, or the original idea was conceptually, we can think about an analog to this situation by one of the fish getting swept down through a horizon where the speed of the water exceeds the speed of sound in the water. And the last phonon will reach infinity. And so the way Unruh describes it is that this is the professor fish and this is his graduate student.
Wouldn't it be the other way around?
And so the really amazing thing that Unruh showed is he thought of this analogy, but then he actually showed mathematically you can transform, and it's quite complicated, the equations of fluid dynamics to have the form isomorphic to the equations to the short geometric impact. And then you can rerun the Hawking calculation for a scalar field and basically rederive the Hawking flux, but we now think of it as a thermal phononic flux associated with a sonic horizon. So I started working on kind of conceptual and philosophical issues related to analog gravity 3 or 4 years ago, and what's been really exciting is that last year, someone actually built one of these things, not out of a fluid, because it's proved very difficult, but out of a Bose-Einstein condensate, which in a certain limit has the same equations as the fluid, and then because fluids have the same equations as relativity theory, you can run the same argument for a BEC. And what Steinhauer did in his lab in Israel is actually show that there's correlation between Hawking modes coming out of the sonic horizon and modes that fall in. And so he showed at least that there is a quantum flux coming out of these sonic horizons. And what was interesting is it was a huge result. It was in papers everywhere. But when you talk to physicists about it, they seem to have very diverse reactions. Some seem to think this is the best thing since sliced bread. Some people seem to think it's a kind of amusing, fun thing to play with, but tells us nothing at all about what's actually going on in black holes. So what I wanted to do, or what I want to do in the last part of the talk, is kind of situate the problem of trying to understand the inferences involved in thinking about, or using this experiment to tell us something about real black holes by comparing it to the inferences we make in everyday experiments. So Eric Winsberg has written this in a very nice way. He went through this distinction between 2 types of validity. So we just think about completely conventional normal experiment. We have 2 notions of validity that are relevant. So the internal notion of validity, which just relates to whether or not the experiment is genuinely learning about the actual system that they're manipulating. That is, the system's not being unduly disturbed by outside influences. This is just, I think, a basic principle of actually doing an experiment. You're actually reading, or your results reflect what you've done in the experiment, not some kind of aberration in your instrument or something like that. But the really interesting and important point, which is so simple that seems a bit silly to say it, is actually experimental results, if they're only internally valid, really don't tell us very much. That's not really why we do most experiments. We do them because we want to learn about systems that we're not manipulating. And to make that inference, we have to have some other notion of validity. That's which is called external validity, when the information learned about the system being manipulated is relevantly probative about the class of systems that are interested to experiment. So that the thing that I'm experimenting on here in my lab, it can appropriately stand in for a wider class of things out there in the world. And I can make inferences about them based on the experiment that I'm doing. The point is, once you get to the point of refining your analysis of conventional experiments to have the step of external validity, conceptually, although practically it's a big move, conceptually it's not much more of a move to think, can we have external validities, can we have arguments to establish external validity of analog experiments as analog experiments? What I mean is that as well as conventional external validation, can we provide arguments that the source system, i.e. the dumb hole in Steinhauer's lab, doesn't just stand in for dumb holes in other people's labs, but it stands in for the kind of analog systems as well, i.e. it can stand in for black holes. So obviously the types of argument we have available to externally validate a conventional experiment are going to be more varied and plentiful and available and respectable than those we might have to validate an analog experiment as an analog experiment. My claim is just that in both cases we are using additional theoretical machinery to make these inferences, and there isn't a difference of kind between the two cases. So the question is then, are there arguments that can externally validate these analog experiments? And interestingly, although they wouldn't use these terms, this is exactly how the people working on analog gravity think about, at least some of them think about their work. So what, I'll come back to that. What Unruh and Schultzold argued in 2005 paper, and there's various other papers arguing from slightly different perspectives, is that the Hawking effect can be understood as a universal phenomena, and we can use this particular argument they have using generic insensitivity to modification of the dispersion relation to justify the claim that it's a universal phenomena. And because it's a universal phenomena, we can make these inferences about black holes based on experiments in dark holes. And so what I want to do is not really say anything particularly more than they were saying, but frame this kind of idea that the people working in analog gravity have that justifies why they're doing what they're doing, with a little bit more reference to kind of discussions, relevant discussions in philosophy and physics. In particular, I think it's quite interesting to think about this observation that Bafferman made quite a while ago now, that we really should think about universality when we find it in the case of critical phenomena as multiple realizability in the sense of Fodor. And he made, obviously in this case, that we have very strong theoretical arguments and experimental results to justify these universality arguments based on renormalization group methods. But the claim is that there's something similar going on in the case of the universality arguments that Unruh and Schultzold made. So if we adapt Bafferman's notion of universality of multiple realizability to the Hawking case, then specifically what they're trying to establish is the following: that the details of the microphysical structure, they call it the trans-Planckian structure, for a reason I probably won't go into, but I can later if you want. The details of the microphysical structure of a given black hole or analog system. So for the fluid, think about it as the details. The fluid model assumes that the fluid's continuum hydrodynamics doesn't have any structure of the molecules. So the details of how the molecular physics of water works, or the details of how quantum gravity with black holes works, are relevant for describing the thermal properties exhibited by the relevant horizons, i.e. the event horizon in the case of the black hole, or the sonic horizon in the case of the dumb hole. And then, two, different realizations of the analog or black hole system with distinct microphysical structure have causal horizons that generically exhibit the Hawking radiation. So I'm not, like, these arguments, there are very strong assumptions that go into them, and I'm not necessarily saying that in the form that they're presented in 2005 or the most recent forms that we're kind of forced to believe in them. But the point is, if we do believe in them, or if we give some kind of non-trivial credence to them, we can start making these kind of inferences. So we're actually also working on a Bayesian model with Stefan Hartmann, where we're trying to frame this in that kind of framework. I won't talk about that more here. So if we have these universality arguments, if we believe them, what they do is they function as external validation for the analog dumb hole experiments. And well, when we interpret them in this kind of metaphysical sense of establishing multiple realizability. So they give us a theoretical basis to take the analog black hole source systems to stand in for a wider class of target systems, including astrophysical black holes. So this seems like a kind of exotic, weird example, but in fact it's actually quite a kind of special case of something fairly mundane. So we think about when we're using, or what kind of arguments function as external validation in typical experiments. Often they're actually things like membership of the same natural kind. So the idea is that's the kind of metaphysical posit that would play a similar inferential role in external validation of conventional experiments that the universality arguments play in this particular. So, to finish, I think that there are good reasons to follow Stein in asserting there's no substantive difference between a cogent and enlightened realism and a sophisticated instrumentalism. And I think in doing so, we open up a challenge to provide, or an opportunity to provide a positive story about what role metaphysical posits do play in scientific practice. And so my two examples were designed to show how we can naturally meet this challenge by thinking about heuristic and inferential roles of metaphysical posits in contemporary theoretical physics. And I want to say this with a pinch of salt. Plausibly, I think metaphysical posits that can't play either this heuristic or this inferential role should be ignored in scientific discourse and mature philosophy. Thank you very much.